Good afternoon, friends. In the previous class, we have discussed the derivation of the Hartnell governor, and in today's class, we are going to solve 2 to 3 problems on Hartnell governor. So let us understand the problem statement first. So the problem statement is, in a Hartnell governor, the extreme radii of rotation of balls are 40 mm and 60 mm, and corresponding speeds are 210 rpm and 230 rpm. The mass of each ball is 3 kg. The lengths of ball and sleeve arms are equal. Determine the initial compression and constant of central spring. So this is the problem statement. So I am solving the problems from SS Ratan, and the problem is given in page number 571. So you can also go through the problem statement once again. So in the problem statement, it is given that the extreme radii of rotation of balls are 40 mm and 60 mm. So it means two radiuses are given. So that is R1 is equal to 40 mm and R2 is equal to 60 mm. So I am going to write the given data. So R1 is given, that is 40 mm, and R2 is given, that is 60 mm. Corresponding to the speeds are 210 rpm and 230 rpm. So there are two speeds. One is N1, that is 230 rpm, and there is another speed, that is N2, that is N1 is 210 rpm and N2 is 230 rpm. The next what is given? The mass of each ball is 3 kg, that is the small m. The ball mass is given as 3 kg. The lengths of ball and sleeve arms are equal. So if I consider the figure for the Hartnell governor or configuration for the Hartnell governor, so this will I call it as B, and this is I call it as A, and this is the ball. I have considered one half of the governor. So this length is B and this length is A. This is the mass ball, and if this is the axis, so this radius is given. This is the radius. There are two radiuses. One is R1, that is the 40 mm, and in another case the radius is increased, that is R2 is equal to 60 mm. So what he has given at the end of the problem statement, the lengths of the ball and sleeve arms are equal. So that means A and B are equal. So he has given that A and B are equal. So A is equal to B or B is equal to A. Both are same. And what he has given and what he has asked, determine the initial compression and constant of the spring, constant of the central spring. So first one is spring constant. Yes, we need to find out. And initial compression he has asked. Initial compression is nothing but Fs1. So these two things we need to find out from the given problem statement. So these are the given data. R is given, that is R1 and R2. N1 is given, N2 is given, mass is given, the lengths of the ball and sleeve arms are given, that is A is equal to B, and we need to find out S and we need to find out initial compression. So initial compression and spring constant we need to find out from the given data. So let us understand how to solve this problem. Let us understand how to solve this problem. So let us go for the solution. Let us go for the solution. Let us go for the solution. So what we need to find out first? First we need to find out the value of the F, that is nothing but spring constant. So we need to find out first the spring constant, and the spring constant is given by S, and the equation for the spring constant we have derived in the previous class. So what is the equation for the spring constant? The equation for the spring constant is 2 into A by B whole square into bracket F2 minus F1 divided by R2 minus R1. So this is the equation which we have derived in the previous class. So to get this equation, so to get the solution of the spring constant, we should have all the values so that we can substitute into the governing equation and we can find out the value of the spring constant. So if I observe the equation, I have A and B values known because A is equal to B, so this becomes 1. R2 value is known, R1 value is known, but the values of F2 and F1 are not known to me. So how to get the values of F1 and F2? So F1 is equal to M1 R1 omega 1 square and F2 is equal to M2 R2 into omega 2 square. So that is nothing but the centrifugal force which is acting radially outwards on the mass of the ball in the governor, which we have seen in the previous case. So this centrifugal force can be obtained by mr omega square, as it is a F1, so I am marking it as M1 R1 omega 1 square, and F2 is equal to M2 R2 omega 2 square. So this is the equation. By this equation I can get the value of F1 and I can substitute the value of F1 here, and to get the value of F2, this is the equation, that is M2 R2 into omega square, so that I can get the value of F2 and I can substitute the value of F2 into our governing equations. So now if I observe these two equations, in these equations also there is one unknown. So M1 is known, R1 is known, M2 is known, R2 is known, but omega 1 and omega 2 are not known to me. So it means omega 1 and omega 2 I need to find out. So how to get omega 1? Omega 1 is equal to 2 pi n1 divided by 60, and omega 2 is equal to 2 pi n2 divided by 60. So this is the equation we have to find out the value of omega 1 and omega 2. So in this equation all are known, pi is a constant, n1 is given, and similarly in omega 2, 2 pi n2 by 60, where 2 pi and 60 are constant, n2 value is already given in the problem statement. So substitute the values of n1 and n2 and get the value for omega 1 and omega 2. So 2 into pi into the value of n1 is given. The value of n1 is how much? 210. So it is 210 divided by 60. So you are going to get the value of omega 1 as 22 radian per second. So you got the value for omega 1 as 22 radian per second. Next, go for omega 2. The equation to get the value of omega 2 is 2 pi n2 divided by 60. So it is 2 into pi into n2 is how much? 230 divided by 60. So this is equal to, we get the value of omega 2 as 23.04 radian per second. So it means I got the value of omega 1 and I got the value of omega 2. So now substitute the value of omega into governing equation of m1 r1 omega 1 square. As the mass of the ball is going to remain same, so for m1 and m2 we have to take the same value of the mass. The mass is not varying, but the r1 and r2 values are varying, omega 1 and omega 2 values are varying. So substitute the value of m1 r1 and omega 1. The value of m is 3 kg. The value of r1 is given in terms of mm. I need to substitute it in terms of meters. So r1 is 40 mm, so it becomes 0.04, and next one is the value of omega 1. The value of omega 1 already we have calculated, that is 22, so it is 22 square. So we can get the value of F1, and the value of F1 is 58.1 Newton. The value of F1 is 58.1 Newton. Similarly, we can calculate the value of F2 also. The value of F2 is m2 r2 omega 2 square. So m is nothing but it is the mass of the ball, which is same for both the cases, that is 3 kgs. R2 value, it is given in terms of mm. I need to convert it in terms of meters, and then I am going to substitute it here, and then substitute the value of omega 2, that is the 23.04 whole square. So you are going to get the value of F2 as 95.6 Newton. So you got the value of F2 as 95.6 Newton. So now if I consider the equation for the spring constant, that is given as 2 into a by b whole square into bracket F2 minus F1 divided by R2 minus R1, where a and b values are known, R2, R1 are known, and F1 and F2 also we have calculated. So each and every term in the spring constant equation is known. Now I can substitute all the values into the governing equation of the spring constant, and I can calculate what is the value of spring constant. So I will substitute all the values, 2 into a by b. So a is equal to b, so I will substitute it as 1 whole square into bracket F2 minus F1, that is the 95.6 is the F2 value, and the value of F1 is already calculated, that is the 58.1. So I will substitute the value of F1 divided by R2 minus R1. R1 and R2 are known to me, so substitute the values of R2 and R1. So 60 minus 40, so you are going to get the value of the spring constant as 3.75 Newton per mm. So this is the value for spring constant, which has been asked as the first question. I hope everything is clear. The first question asked is to find out the spring constant. So to get the value of the spring constant, we have the equation S is equal to 2 into a by b whole square into bracket F2 minus F1 divided by R2 minus R1. This is the equation which we have derived in previous class, that is the derivation for Hartnell governor. So in this equation, a, b, R1, R2 values are known, only F1 and F2 values are unknown. So that is the reason why I have calculated the value of F1 and F2 using the equation m r omega square. So in case of omega 1 and omega 2, I need to use the equation 2 pi n1 by 60 and omega 2 is equal to 2 pi n2 by 60. By substituting all the values of n1 and n2, I got the values of omega 1 and omega 2. Now then I have substituted the value of omega 1 into the F1 equation and omega 2 value into F2 equation. I got the values for F1 and F2. Then I have substituted these values of omega 1 and omega 2 into my governing equation for spring constant, that is S is equal to 2 into a by b whole square into bracket F2 minus F1 divided by R2 minus R1. By substituting all the values and by calculation, I got the value for S as 3.75 Newton per mm. So this completes our first question, that is to calculate the spring constant. So now let us go for the second question, that is initial compression. Initial compression. we need to find out the second question, that is what is the value for initial compression. So initial compression, the equation for initial compression, to get the value for initial compression, we have to use the equation which we have derived, F1 into A is equal to 1 by 2 into bracket mg plus Fs1 plus F plus mg into C1, mg into C1. So in this equation, we need to get the values of, sorry, this is multiplied with B. So in this equation, we consider that by neglecting the obliquity of the arms, if I neglect the obliquity of the arms, then this C1 becomes 0. So this entire term mg into C1 whole term becomes 0. So the remaining equation is F1 into A is equal to 1 by 2 into bracket mg plus Fs1 plus F into B. So this is the equation which I am going to remain with. Okay, so this is the equation which I am going to remain with. Then next term is to get the value of the initial compression. I need to get the value for the initial compression. So in this governing equation, the value of capital M, that is the mass of the sleeve, is not given, so I can take it as 0, and the force of friction is also not given, so I can take it as 0. So the remaining equation is F1 into A is equal to 1 by 2 into Fs1 multiplied with B. So this is the equation which I am going to remain with. So now in this case, A and B are same, so they both cancel out or is equal to 1. A by B is equal to 1, so A is equal to B. So I will be remaining with F1 is equal to 1 by 2 into Fs1. The remaining term is F1 is equal to 1 by 2 into Fs1. So the value of Fs1 is equal to 2 into F1. The value of Fs1 is equal to 2 into F1. So I know the value for F1, so I can substitute the value of F1 here. So this is 2 into F1 is how much? It is 58.1. So multiply it with 2, so you will be remaining with 116.2 Newton. 116.2 Newton. So therefore, now I can find out initial compression is equal to Fs1 divided by S. That is the equation to find out the initial compression. So we have the value for Fs1, that is 116.2 divided by, you know, the value for S, that is 3.75. So I can calculate, and the final value for initial compression is 31 mm. 31 mm. So this completes the problem and also the solution for the second question, that is to find out initial compression. So once again I will explain the problem. You can go through it. So in the initial problem statement, the data given is R1 as 40 mm and R2 as 60 mm. And also they have given us two speeds, that is N1 is equal to 210 RPM and N2 is equal to 230 RPM. And also the mass is given, that mass is nothing but mass of the balls. I can mention it as MB if there is any confusion. So usually small m is going to represent the mass of the ball and capital M is for mass of the sleeve. So mass of the ball is given as 3 kg, and also they have mentioned in the problem statement that the length of the ball and sleeve arms are equal. The length of the ball and sleeve arms are equal, so it means A is equal to B. So using this data, what we need to find out is the spring constant S and the initial compression we need to find out. Sorry, not Fs1. We need to find out only the initial compression. By mistake I have written it as Fs1. It is not Fs1. The Fs1 we need to find out to get the value of the initial compression. So let us understand the solution part. So we know the equation for spring constant. To get the value of the spring constant, we have the equation which we have derived in the previous class of derivation of Hartnell governor, where we have derived the equation for S, that is nothing but S is equal to 2 into A by B whole square into bracket F2 minus F1 divided by R2 minus R1. So if I analyze this governing equation for the spring constant, A and B values are known, that they are equal. He has clearly mentioned the lengths of ball and sleeve arms are equal. R2 and R1 values are known, but only unknowns in the equation is F1 and F2, which are not known. So it means that to get the value of the spring constant, we need to find out the value of F1 and F2. So how to find out the value of F1 and F2? So to get the value of F1 and F2, we need to understand what is F1 and what is F2. F1 and F2 are the centrifugal forces which are acting radially outwards on the mass of the ball. So for centrifugal force, we have the equation F is equal to mr omega square. So as there are two forces, I am going to represent it as F1 and F2. So the terms associated with F1 and F2 as m1 r1 omega 1 square, and the terms associated with F2, I will name it as F2 is equal to m2 r2 omega 2 square. So in this equation also, we don't have the values for omega 1 and omega 2. To get the values of F1 and F2, we should know all the values of the terms which are associated in this equation. We have the value for mass of the ball, we have the radius, but we don't have the value for omega. So to get the value of omega, I am going to use the equation omega 1 is equal to 2 pi n1 by 60 and omega 2 is equal to 2 pi n2 divided by 60. So 2 pi is a constant value, 2 into multiplied with a constant pi, and the value of n1 is known, that is 210 divided by 60, and omega 2 is equal to 2 into constant pi into n2, that is nothing but 230 divided by 60. I got the value of omega 1 as 22 radian per second and omega 2 as 23.04 radian per second. So substitute these values of omega 1 and omega 2 into the equation of centrifugal force, where m1 is known, that is 3 kg into r1, that is of 40 mm. I am going to substitute in terms of meters, and omega 1 as 22. So similarly substitute the values of m2, r2 and omega 2, you get the values of f1 and f2. So now substitute these values of f1 and f2 into governing equation. 2 into a by b whole square, as a and b are same, so it becomes 1. So f2 is 95.6 minus f1 is 58.1 divided by r2 is 60 minus r1 is 40. So I get the spring constant as 3.75 Newton per mm. Next question is to find out the initial compression. To get the value of initial compression, I need to use the equation Fs1 by S. Fs1 why I am using, because it is the initial compression. So that is why I am using Fs1. So to get the value of initial compression, I can use the equation Fs1 by S. To get the value of this initial compression, I should know all the values of Fs1 and S. In the previous problem, in this problem only, in the first part, I have calculated the value of S, but I don't know what is the value of Fs1. So how to get the value of Fs1? So to get the value of Fs1, I will use the equation, that is F1 into A is equal to 1 by 2 into mg plus Fs1 plus F into B plus mg into C1. By neglecting the obliquity of the arms, C1 multiplied with m into g becomes 0. The remaining term is F1 into A is equal to 1 by 2 into mg plus Fs1 plus F into B. In this problem, the mass of sleeve is not given, so I will take it as 0. And the force of friction is also not given, so I will take it as 0. Then these two terms becomes 0. The remaining term will be F1 into A is equal to 1 by 2 into Fs1 into B. Now, we know that the lengths of ball and sleeve arms are equal, so A is equal to B, they both cancel out. The remaining term is F1 is equal to 1 by 2 into Fs1. So I need to get the value of Fs1, so multiply 2 to this side, so it becomes Fs1 is equal to 2 into F1. So 2 into F1 value is already known, that is 58.1. So substitute, you are going to get the value of Fs1 as 116.2 Newton. So final equation for initial compression is given by Fs1 by S. So Fs1 we have calculated, that is 116.2 divided by the spring constant S we have calculated, that is 3.75. So you get the value for initial compression at 31 mm. So this completes the problem number 1. So next let us discuss the problem number 2. Let us discuss the problem number 2. So second problem also I am going to solve it from Ratan only. Page number is same, that is 571. I will go through the problem statement. So just understand what is given in the problem statement. In a spring-loaded governor of the Hartnell type, the lengths of the horizontal and vertical arms of bell crank lever are 40 mm and 80 mm respectively. The mass of each ball is 1.2 kg. The extreme radii of rotation of balls are 70 mm and 105 mm. The distance of fulcrum of each bell crank lever is 75 mm from the axis of rotation of governor. The minimum equilibrium speed is 420 rpm and maximum equilibrium speed is 4% of higher than this. Neglecting the obliquity of arms, determine first one the spring stiffness, second one initial compression, and third one equilibrium speed corresponding to the radius of rotation of 95 mm. So this is the problem statement for the second question. So first let us understand what is given in the problem statement. So once we understand what is given in the problem statement, then we can easily understand what are the missing terms, so that we can find out them and we can get the solution of spring stiffness, initial compression, and equilibrium speed of the governor. So first I will write is given in the problem statement. So that is nothing but given data. In a spring-loaded governor of Hartnell type, the lengths of the horizontal and vertical arms of the bell crank lever are 40 mm and 80 mm respectively. So please understand what is given. Lengths of the horizontal and vertical arms. So lengths of the horizontal and vertical arms. So these are the arms. So here I will be having a mass ball or a ball. So lengths of the horizontal and vertical arms. So horizontal arm, how I have mentioned, what is the notation for the horizontal arm? In the previous derivation, if you go through the derivation of the Hartnell governor, the horizontal arm we have mentioned it as B and vertical arm we have mentioned it as A. It is clearly denoted in the derivation of the Hartnell governor. So please go through the derivation of the Hartnell governor, you will come to know. So in this problem statement what he has given, the lengths of the horizontal and vertical arms of the bell crank lever are 40 mm and 80 mm. So B is 40 mm and A is 80 mm. So that is given. So I will write A as 80 mm and B as 40 mm. Next, what is given? The mass of each ball is 1.2 kg. So this mass of the ball is 1.2 kg. So I will mention it as small m, that is 1.2 kg. Next, the extreme radii of rotation of the balls are 70 mm and 105 mm. The extreme radii of rotation. So if this is the axis, then this is R1, and R1 is given as 70 mm, and there is one more extreme radius, that is R2, that is nothing but 105 mm. So this is the problem statement in which it is given. The distance of the fulcrum of bell crank lever is 75 mm from the axis of rotation of the governor. So let us see what is that 75 mm afterwards. The minimum equilibrium speed is 420 rpm and the maximum equilibrium speed is 4% higher than this value. So instead of giving the N1 and N2 value, he has given only the value of N1. The value of N1 is given 420. But the N2 value is not given, but he has mentioned in the problem statement that N2 is 4% higher than N1. 4% higher than N1. So that is given in the problem statement. Then, neglecting the obliquity of the arms. He has clearly mentioned this problem statement is very, very important. Neglecting the obliquity of the arms. So please understand, neglecting the obliquity of the arms means mg into C1 is not going to come into picture. So it means that the governor is in the mean position. Determine the spring stiffness. What he has asked? He has asked us to find out the spring stiffness. He has asked us to find out the initial compression and also equilibrium speed corresponding to radius of rotation of 95 mm. So let us understand how to solve this problem. The problem is very simple and very easy, and it is similar to the previous problem also, but a small change in the problem. So to get the value of the first one is asked as spring stiffness. First one they have asked as spring stiffness, and that is nothing but S. The equation for spring stiffness is already known, that is S is equal to 2 into A by B whole square into bracket F2 minus F1 divided by R2 minus R1. So this is the governing equation. So in this, A value is known to us and B value is known to us. R1 and R2 is known to us, but F1 and F2 is not known. So it means first we need to find out the value of F1 and F2. So F1 is equal to M1 R1 omega 1 square and F2 is equal to M2 R2 and omega 2 square. So in this also M1 R1 M2 R2 is known, but omega 1 and omega 2 is not known to us. So it means we need to calculate first omega 1 and omega 2 so that we can get the value of F1 and F2. So calculate the value of omega 1. So omega 1 is given by 2 pi n1 divided by 60. So 2 into constant pi into n1 is known to us. So n1 is given here in the problem statement, that is 420 divided by 60. So you get the value for n1 as 44 radian per second. So to get the value of omega 2, so what he has said in the problem statement, the minimum equilibrium speed is 420 rpm and maximum equilibrium speed is 4% higher than this. So already I have got the value for omega 1, so directly I can calculate the value for omega 2. So I know the value for omega 1, that is 44, and to get the value of omega 2, so whatever you have got, the omega 2 is 4% higher than this, so I will multiply it with 1.04, so I will get the value for omega 2, and the value for omega 2 is 45.76. radian per second. The value for omega 2 is 45.76 radian per second. Next is calculate the value of F1 and F2. So F1, M1 R1 omega 1 square is the equation. The mass of the ball is given, that is 1.2, multiplied with R1, that is nothing but 70 mm. So 0.070 into omega 1 is 44. So you get the value for F1 as 162.6 Newton, and similarly calculate the value for F2, that is nothing but M2 R2 into omega 2 square. So M is constant, that is 1.2. R2 is how much? 105 mm it is. So I need to substitute in terms of meters. So 0.105 multiplied with omega 2 is 45.76 omega 1 square. So this is square. So this becomes the value of F2 as 263.8 Newton. So you got the value for F2 as 263.8 Newton. So now you have all the values for S. So use the equation S is equal to 2 into A by B whole square into bracket F2 minus F1 divided by R2 minus R1. So substitute all the values. So S is equal to 2 into the value of A and B is known to us. A is 80, B is 40. So 80 divided by 40. So F2 value is known, 263.8 we have calculated, minus F1 is 162.6 divided by the value of R2 and R1 is given. R2 is 105 and R1 is 70. 5 minus 70. So with the help of calci, substitute all the values and get the value for S. The value for S is 23.14 Newton per mm. So this is the value for spring constant or spring stiffness. Yes. The next thing is second question. Let us go for the second question. So what is asked in the second question? They have asked us to find out the initial compression. So the second question is to calculate the initial compression. So what is the equation to calculate the initial compression? That is nothing but Fs1 divided by S. Fs1 divided by S. So that is the equation to get the value of initial compression. So in this equation, S is known, but Fs1 is not known to us. So it means first we need to calculate the value of Fs1. So how to get the value of Fs1? So we know the equation F1 into A is equal to 1 by 2 into bracket mg plus Fs1 plus F multiplied with B plus mg into C1. So this is our equation which we have seen in the derivation of the Hartnell governor. But here what he has given in the problem statement clearly, that neglecting the obliquity of the arms. So if I neglect the obliquity of the arms, then this whole term becomes 0. So why it becomes 0? We have already seen that becomes C1 is equal to C2, and C1 is equal to C2 is nothing but it is a 0. If there is no any displacement, then it becomes a 0. The remaining equation now is F1 into A is equal to 1 by 2 into bracket mg plus Fs1 plus F divided by 2 into B. So this is the remaining equation now. So in this equation, we know that A is equal to 2B. A is equal to 2B because A is 80 and B is 40. So it means A is 2 times of B, right? So A is 2 times of B. So I will substitute it. So F1 into 2B is equal to 1 by 2. So here the mass of the sleeve is not given, so I will take it as 0. So 0 into G becomes 0. The force of friction is also not given, so I will take it as 0. The remaining term is Fs1 divided by 2 multiplied with B. So now what is remaining for F1? So F1 is equal to Fs1 divided by 4. So Fs1 is equal to 4 into F1. Fs1 is equal to 4 into F1. So F1 is known. So that is, what is the value for F1? That is 162.6. So you can get the value for Fs1. The value for Fs1 is 650.4. The value for Fs1 is 650.4. So now all the values are known to me. So I can calculate what is the value for initial compression. So what is the value for initial compression? So substitute all the values here. So Fs1 is 650.4 divided by the value of S is calculated, that is 23.14, and you get the value for Fs1 as 28.1 RPM. So this completes the second question for the second problem. So here there is no any two term, so by mistake I have taken this. So it is only 1 by 2 into mg plus Fs1 plus F divided by 2. That is it. Here I have taken on extra 2, that is not there. By mistake I have taken. Please don't take it. This is the equation. This is what the equation we have. Next, in the third question, what he has asked is, determine the equilibrium speed. Corresponding to a radius of rotation of 95 mm. So we have calculated for R1 and R2 and N1 and N2. Now what is asked is equilibrium speed corresponding to a radius of rotation of 95 mm. So the solution for sub question number 3 can be as it is. So let F3 be the corresponding force. Let F3 be the corresponding force at R3 is equal to 95 mm. Let F3 be the corresponding force at R3 is equal to 95 mm, because what he has given, equilibrium speed corresponding to a radius of rotation. So another radius of rotation is given, that is R3 is equal to 95 mm. So for a radius R1, the corresponding force is F1. For radius R2, the corresponding force is F2. And similarly, for radius R3, let F3 be the corresponding force. So now the equation for S is given by S is equal to 2 into A by B whole square into bracket. So it is F2 minus F1 for radius R1, R2, the forces were F1, F2. So we have written it as F2 minus F1 divided by R2 minus R1. Now the radius is R3. So it means its corresponding force is also F3. So the equation can be written as F3 minus F1 divided by R3 minus R1. So this is our equation now to find out the value of the S. So we know the value for S, that is 23.14. So 2 into A by B is, A is 80, B is 40 divided by 2. F3 is not known to me. I need to find out what is the value for F3. F1 is known, that is 162.6 divided by R3 is given 95. minus R1 is given in the problem statement, that is 70. So all the values are known except F3 in this particular problem. So I can find out what is the value for F3. So by substituting all the values, I can get the value for F3 as 234.9 Newton. So this is the value for F3. So once you know what is the value for F3, so what is asked in the problem statement? Equilibrium speed they have asked. So once you know the value of F, you can find out the value of N. So how to get it? F3 is equal to M3 R3 into omega 3 square. So that will be the governing equation. So F3 is known, that is 234.9. M3 is nothing but, once again, the mass of the ball which is given, that is nothing but 1.2 kg. That will be same. R3 is given, that is the 95 mm it is. So I need to substitute in terms of meters. So 0.95 into omega 3 square. So all the values are known, only omega 3 square is not known. So by using the calculator, I can calculate the value for omega 3 as 45.393. So once I calculate the value of omega 3, I can calculate what is the value of the speed. So how to get omega 3 is equal to 2 pi n3 divided by 60. Omega 3 is equal to 2 pi n3 divided by 60. So omega 3 value is known, that is 45.393, which is equal to 2 into pi constant. N3 I need to calculate divided by 60. So all the terms are known, only N3 is unknown. So calculate the value of N3, and it is N3 is 433.5 RPM. So this completes the problem number 2 on Hartnell governor. So once again I will explain from the beginning, just go through it. The lengths of horizontal and vertical arms are given as A is equal to 80 mm and B is equal to 40 mm. The value of M is given as 1.2 kg, that is nothing but the mass of the ball. R1 and R2 is given as 70 and 105 mm. N1 is given, N2 is 4% higher than this. What is the value of spring stiffness and what is the initial compression? So spring stiffness is given by equation S is equal to 2 into A by B whole square into bracket F2 minus F1 divided by R2 minus R1. So all the values are known, F1 and F2 are unknown to me. So I find out the value of F1 and F2 using the equation MR omega square. So omega you can get by using the equation 2 pi nt by 60. So you get the value for omega 1 as 44. So omega 2 is 4% higher than this value of omega 1. So 44 into 1.04, it becomes 45.76. So substitute all the values into the governing equation. You are going to get the value for spring stiffness as 23.14 Newton mm. So this is the spring stiffness. The next what we need to find out is initial compression. So initial compression is given by Fs1 by S. That is the governing equation for Fs to calculate the initial compression. So S value is known, but Fs1 value is not known. So because of that, we are going to use the equation which we have used in the derivation of the Hartnell governor. That is F1 into A is equal to 1 by 2 into mg plus Fs1 plus F into B plus mg into C1. As it is given in the problem statement that by neglecting the obliquity of the arms, we need to calculate what is the initial compression. So if I neglect the obliquity of the arms, this mg into C1 becomes 0. The remaining term is F1 into A is equal to 1 by 2 into mg plus Fs1 plus F into B. So in this equation, the mass of the sleeve is not given, so I will take it as 0. This entire term m into g becomes 0. The force of friction is not given, so I will take it as 0. The remaining term is F1 into A is equal to 1 by 2 into Fs1 into B. So if I consider the given data, A is 2 times higher than B. So A is equal to 2B. So wherever A is there, I will substitute as 2B. F1 into 2B is equal to 1 by 2 into Fs1 into B. That is the equation. So BB gets cancels out. So F1 is equal to 1 by 4 into Fs1. So Fs1 is equal to 4 into F1. So Fs1 is equal to 4 into F1 is calculated as 162.6. So you get the value of Fs1 as 650.4. So now substitute this value of Fs1 into the equation of initial compression, that is Fs1 by S. So it becomes 650 divided by S. Already you have calculated as 23.14. So you will get the value of initial compression as 28.1 RPM. The next third question is, what is the equilibrium speed when the radius is 95 mm? He has asked, the third question is, if I change the radius from given values to 95, then what will be the equilibrium speed? When the radius is 70 and 105, I know what is the value for speed, N1 and N2. But if I change the value of R and if I make it as 95 mm, then what will be the value of the corresponding speed? So to get the value of corresponding speed, once again I am going to use the spring stiffness equation, that is S is equal to 2 into A by B, F3 minus F1 divided by R3 minus R1. So S value is known, A and B values are known, F3 is unknown, F1 is known, R3 is known, R1 is known. So you can calculate the value of F3. So once you calculate the value of F3, I can use the equation F3 is equal to M3 R3 omega 3 square. So omega 3 is unknown in this, you can calculate value of omega 3. Once you calculate the omega 3, then use the equation omega 3 is equal to 2 pi N3 by 60. And then you can calculate the value of N3 as 433.5 RPM. So this completes the problem on Hartnell governor. That is second problem. In the next class, I am going to solve one more problem on Hartnell governor, and that completes all the portions on governors, that is Porter governor and Hartnell governor, and we will start with the vibration part. Okay, thank you.